Okay, so capacitor is basically a charge storage unit. Charge builds up in the capacitor, and then we might be able to use it for another circuit, for another item, to do a certain job. It may be there to protect a circuit from over current. So like a surge protector might have a capacitor in it to pull extra current when, or pull extra charge when there's a surge on the line. So let's look at some capacitors. Here's the simulation. There's a battery, looks like a Duracell. These are two parallel plates. Okay, so parallel plates will store the charge. There's no connection between these two plates. But I'm going to take the battery, and if I turn up the voltage, now, do you see the blue arrows that show up just briefly and then kind of fade away? They only show up while there's charge moving. So when we open up the gates or increase the voltage, truly negative charges flow, because the electrons are the ones that move. The negative charges flow and start filling up this space. All right? Those negative charges repel the negative charges of the electrons that would be in this metal plate, and they take off and go this way, leaving behind positive charges. So I've got little red positive charges up here, blue negative charges down here, and for every negative charge there's a positive charge. So what exists between two oppositely charged plates? Do you remember? How about an electric field? So they're stuck in the electric field. So as I raise the voltage up, what's happening to the amount of charge on the plates? Do you see that we have a lot more charge? What happened to the field lines? Did it get more dense? Maybe stronger between the two plates? All right, if I lower the voltage, it becomes weaker and weaker to 0. And notice as I was lowering the voltage, the direction of the negative charge flow changes. I increase it, decrease it, they change. So that's not the direction of conventional current. That's the direction of electron flow. Conventional current is exactly the opposite. It's what would your positive test charge do? Conventional current. Okay, so let's see. This is the capacitor. It's like a warehouse. How could I change this warehouse so it could hold more charge? Any ideas? I can make it bigger. What if I make this area bigger? What's happening to my positive charges? Are there more on there? Looks like, what, 9? Is that more than 9? Yeah. So by increasing the area of the plate, I've got more capacity for the capacitor. Capacity, that's where it comes from. Okay, so think about adding on to a building or adding more seats to a stadium. We increase the capacity. Okay, so that means, we'll hop over here, that means that our capacitance should be directly related to the area, the cross-sectional, or the area of the plate. And this isn't the area of both plates, this is the area of a plate. Of one plate. So don't double it. Rookie mistake is to double it. So area of one plate. Okay. Alright, so let's go back, and I'm going to make this area normal again. Now I can change the separation distance. What if I put them closer together? What's happening to our positive charges on there? Increased. So let's think about this. Okay, positive charges and negative charges really like each other. They really want to be together. But negative charges and negative charges, they don't like each other. So as I decrease the distance between these two plates, it's like their desire to be closer to the opposite charge is greater than the repulsion with the equal charges. So they scoot really close together so that there's enough room for everybody to get in there and be attracted to those opposite charges. So it actually pulls, because of the electric force between the two, pulls more charge onto the plates. So by bringing the plates closer together, we can actually increase Okay, so this is the distance between the two plates. And distance would be measured in meters. And what about area? Let's hop back up here. What would area be measured in? Meters squared. Okay, great. Now there's one other component to this capacitor. If I hop back over here, and that's what's between the two plates. I mean, I know there's an electric field that exists, but what's the stuff between my two plates? Is there anything stuck in between my two plates? I can remove the electric field lines there. What's in between my two plates? Air. Very good. So, how the electric field can permeate that space depends on what material is between your two plates. So if we push a silicone or a ceramic material between the two plates, the electric field set up by the two plates will then affect the protons and electrons in that material, creating an electric field in the opposite direction. And so if you have an electric field down and an electric field up due to the dielectric, then you're going to get a weaker electric field between the two. So you'll get a different capacitance because the affinity for those charges to be there together changes. But we don't have to cover dielectrics in this course, but you do need to consider the fact that there is air between, or no air, pardon me, vacuum between our two plates. And so the constant that we need to use is the permeativity, I said the wrong word, the permeativity of free space. And the symbol is an epsilon, not. Okay, so this is our permeativity, and I'm going to permittivity of free space, and it has a value, and I'm going to write it right above it because I kind of ran out of space. It's 8.85 times 10 to the negative 12, and its units are Coulomb squared per Newton meter squared. So I'm giving you the units there so that we can work our way back to figure out what is the unit for capacitance. So this is our capacitance. And let's look at our units. I'm going to scooch just a hair here. So our capacitance, C, whatever that is, will be equal to Coulomb squared per Newton meter squared. Did I put a square up there? Yeah. I forgot it earlier today, so I had to double check. Times the unit for area, which is m squared, divided by meters. So what's that going to leave us unit-wise? Coulomb squared, definitely, divided by Newton meter. Does anybody remember what a Newton times a meter was? That's a joule. It's energy. That's right. So Coulomb squared per joule if you want to. And that's still a mouthful. So we name this a farad after Michael Faraday. And a capital F is the unit that's used. And 1 farad is a huge capacitor. So most of the capacitances that you will see in problems will be microfarads. Remember the micro symbol? So like 10 microfarads, 3.3 microfarads. You might even see 2 picofarads. Pico is times 10 to the negative 12. So you're probably going to see a prefix that's a times 10 to the negative something in there. Okay? Alright, so let's see, how is capacitance, voltage, and charge related? So let's look back over here at the app. Again, we're going to suspend our disbelief and pretend that we're actually doing this and we can count all the charges on this plate. Okay? So when we're sitting here at 0 volts, I'm increasing the voltage. What's happening to the charge on the plates? Am I getting more red dots or fewer red dots as I'm increasing the voltage? More, increasing. So let's graph that. Wouldn't that look like Q is what we were measuring or looking at versus V? And Q would be coulombs, and voltage is joules per coulomb, or just volts if you want to. Does that seem like a reasonable equation? As the voltage increased, the charge increased? Yeah. So, we could write an equation, right? Q is equal to the slope of that line times the voltage. And the slope of that line being constant is actually what we call the capacitance. So QCV or QVC. I don't care which one you call it. So Q is the charge on one plate. Because hey, what's the total charge on the capacitor? Thank you. So when we talk about the charge on the capacitor, we're actually talking about the charge on one of the plates. Because that's how much charge could move. Okay, or you could talk about being the negative plate. Okay, so this is the charge on one plate. And charge is measured in coulombs. This is our capacitance, sometimes called a cap, especially if you're abbreviating because you're running out of space, measured in farads. And this is your voltage. Measured in volts. So, this is the relationship between charge, voltage, and capacitance. Now there's another relationship that I see between these two variables. What do I get when I multiply coulombs and joules per coulomb? Joules, energy. Okay, so let's think about this. A capacitor stores charge, okay, and that charge can be used. So for example, if you've got the capacitor that you probably don't even think about but you use all the time is a capacitor that's probably in the flash of your camera. So you've got a battery wired to a switch that can close and connect it to a capacitor. The symbol for a capacitor is two double lines, kind of like the parallel plates. Then let's have another switch over here, and then let's connect it to a light bulb. Okay, so now if I close this switch, the charge suddenly starts flowing, and truly our negative charge builds up on the bottom, and our negative charges on the top plate are pushed away, leaving our positive charges there. But the positive side of the battery will be polarize the top of the capacitor to be positive because it's connected to the positive side of the battery, and the negative side of the battery is connected to the bottom side of our capacitor, so it will be negative. So positive to positive, negative to negative. Now, it's all charged up. If I open that circuit and then I close this one right here, it's like you're suddenly, you put a bridge between the boys and girls camp. They don't have to cross the lake anymore. The lake, you know, the impassable lake, the bog of eternal stench that nobody wanted to go into. So what are the electrons going to want to do? They're going to go woo as fast as they can. That's the electron. So what's the conventional current going to do? The other way. What would your positive test charge do? And in that moving, they're going to go through this light bulb. And what's that light bulb going to do? So when that charge leaves the capacitor, runs through the light bulb, we get the capacitor discharges through the light bulb, we get a bright flash of light that's just temporary, and then all the charge has dissipated, and the circuit gets opened again. We can close, all these guys are gone. And then we have to close this one again and let it recharge. Have you ever had a camera that you have to wait for the flash to recharge? Or especially one of those disposable cameras? Are y'all too young to use disposable cameras? Anyway, if it had a flash, you had to like press the button to charge the flash, to charge the capacitor on the flash. And if you've got a fancy camera with a speed light on it, it still has to charge a capacitor, or it may have more than one in there, so you can take lots of pictures at once and use your flash. But it still will have a time where it's not ready. All right, and light is a form of what? Energy. Okay, and when I multiply coulombs and joules per coulomb, I get the unit for energy. So it looks like maybe the area under the curve would be the energy stored in our capacitor. Does that seem possible? So that's the energy stored. So we like to use U for stored energy, and if you want to put a little C beside it for it to represent a capacitor, we can do that. And how can I find the area under this triangle? If this is our voltage V and this is at some charge Q, 1/2 VQ. Usually you'll see it as Q times V because it's like an alphabetical order or something. Now wait a minute, what does Q also equal? CV. Oh, so it would be really handy for us to make a substitution. So 1/2 CV times V, so CV squared. Now that's my favorite version of this equation because what does it look like? 1/2 something something squared. 1/2 MV squared. 1/2 KX squared. Oh, do you see the trend? 1/2 constant value. All right, once we put a capacitor into a circuit, we can't change its area. That takes taking it out of the capacitor and redefining it, okay? So think of capacitance as being a constant, that slope there. But we can change the voltage. Put a different battery in the circuit. So 1/2 mass times velocity squared. Usually in our problems, we don't have an object that's changing mass as it's moving. I mean, like a truck leaking or something, you know, we don't have to do that stuff. But but we had our mass that was constant times our velocity that could be different. 1/2 KX squared. 1/2 the spring constant times your variable squared. So that's why I like the 1/2 CV squared, because it looks like the other energy equations. It looks like the form of an energy equation. Like they could be cousins, symbols, all from the family energy. Whatever. Okay, so let's put a box around that guy. I think the top one is the one you get on the AP exam, and the bottom one is one you have to like come up with by substituting that guy in there. But that's your stored energy. Alright, so capacitors in series would kind of look like this. I'm going to hop over here. No, I'm not. Oh my, right here. Okay, so these are two identical capacitors for now, and they are wired in series, and you can see this plate separation, all that stuff in here. And as I increase the voltage, what do you notice about the charge on each plate? Is it increasing or decreasing? Increasing. Are they the same? Yep, 6 and 6, 9 and 9, or 8 and 8, or something like that. Anyway, so more and more charge. Okay, and they both have the same amount of charge? Okay, now let's test. This battery is topped out at 1.5 volts. This is my multimeter. Doesn't it look like the little multimeters you used? I'm going to measure the voltage in parallel, right, across that capacitor, and you probably can't see it, but it's 0.75 volts. So 0.75, and then this one over here is also 0.75. What's 0.75 plus 0.75? 1.5. Okay, so, well, these are two identical capacitors. Let's see, what would it be if we changed our capacitor? So I'm going to bring my voltage back down to 0. And then I'm going to increase this capacitance. By pulling it together, remember, we can increase the capacitance. Now I'm going to crank up the voltage. What do you notice about the charge on each plate? They're increasing again. And equal. Right, Otten? Now let's check the voltage. All right. Again, I'm going to put my voltmeter in parallel to my capacitor, and I get 0.38 volts right here. So for you guys far away, that's 0.38. Now I'm going to move it over here and test it, and it's 1.12. What's 1.12 plus 0.38? 1.5. Oh, so even though they're different capacitors, their voltage still adds up to be the voltage of the battery. But what do you notice about the charge on each one? They're the same. So let's see. We can come up with some rules. So it looks like when they're in series, the total charge supplied by the battery is the charge on 1, which is the charge on 2. They have the identical charges. And it looks like the total voltage is the voltage across 1 plus the voltage across 2. Now we did this with this sort of exercise with the series resistors using Ohm's law. But if Q is equal to CV, then doesn't V equal Q over C? Is that good? So let's substitute Q over C for each one of these voltages. So this would be Q total over capacitance, and I'm going to use the equivalent subscript because I think that's what your book uses. It doesn't matter. You can call it total, complete, whatever. And then this this would be Q1 over C1. This would be Q2 over C2, not equals, plus. So what about QT, Q1 and Q2? They're all the same, so what can I do mathematically? Can I divide them? Whoops. Like that. Alright, so let me scroll down just a little bit. So what's that leave us with? That leaves us 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2 plus 1 over C3 plus 1 over C4 plus 1 over C5, as many as you would have. What does that look like? Resistors in parallel, but this is capacitors in series. So this is caps in series. Capacitors in series. Alright, so now let's look at them in parallel. So over here, I'm going to put 2 in parallel. Grab my voltmeter here. And let's do the same thing. Let's start out with equal capacitance. And our battery is maxed out. If I draw it down, let's see. So as I increase the voltage, each one of the capacitors is increasing in charge. Okay. Now let's see. Let's make C2 bigger. Remember, we reduced, oh my goodness, I kept the voltage the same. I just made the capacitance, the capacity bigger. And now what's on this guy compared to that one? C2 is what? Has a lot more charge on it, okay? But the battery supplied this charge and that charge. So what can we say about the total charge supplied by the battery? Is it equal to the charge on each one? Right? Let's look at the voltage. All right, so 2 different capacitors, same battery. I'm going to grab my voltmeter, wire it in parallel, It says 1.5. All right? And my battery is 1.5 too. 1.5. So what can we say is a rule about voltage across parallel capacitors? They're the same. All right, so let's hop over here. So that means that V total, the total voltage across that branch, is equal to the voltage across one of them, which is the voltage across the second one. Now, Q is equal to CV. So let's make the CV substitution into our Q's here. So I'm going to just come down here, and I'm going to write in my substitutions. So Q total would be C equivalent, C total, whatever you want to call it, times voltage total. Q1 would be C1V1 plus Q2 would be C2V2. I didn't put a 1 there. There we go. What do you know about V total, V1, and V2? And mathematically, what can happen in that equation? Yeah, I can divide by the voltages because they're all the same. So then I'm left with the equivalent capacitance is C1 plus C2. What does that look like? Yeah, that looks like resistors in series, but it's capacitors in parallel. Wow.